In a previous lab using this simple mass beam setup, we focused on simple ways to measure the beam stiffness just by applying static loads on the tip of the beam. We also introduced accelerometer usage. We mounted an accelerometer right on the tip here, and that added some mass. So we had some mass located at the end of the beam, and we also looked at ways by using modeling techniques to estimate how much effective mass of the beam is included when you look at the response of the system. This gave us an opportunity to study second order system response, so hopefully you have a better grasp of those principles, and you estimated the natural, I should say the undamped natural frequency, and measure the damping ratio using an experimental log decrement method. From that, you were tasked with finding the effective B value. So in a sense, this is a simple system that allows you to sort of study the concept of a mass spring damper system model that you're introduced to in many other courses. Another purpose of this lab was to give you more practice using LabVIEW, especially for data acquisition, plotting, and so on. We want to use that same setup in this coming lab. Now what we want to do is introduce force measurement and also characterization of a component. In this case, we're going to add a little air pot damper between the tip of this beam and attach it to this load cell through this little mounting plate. So this little tip here, as you'll see in a related video, can be screwed into this little plate, which attaches then to this load cell. And this load cell is fixed to a base plate that's then basically clamped down to the table. So really, it's a similar system in the sense that it's a mass spring damper system. What we're doing by attaching the damper at the tip load is effectively increasing the overall damping of the system. But because we're measuring the force at one end of this damper, and this is a fixed, essentially fixed end, we can directly measure the damping rather than relying on, say, the log decrement method to infer the B value using the damping ratio of the overall system. So the overall goal of this lab then is to study it, and here you see it realized. We'll be mounting an accelerometer here to measure the acceleration and integrate the acceleration to get the velocity. Here's the air pot dash pot, and here's the strain gauge load cell. So we want to do is study strain gauge principles and also subsignal processing techniques. Here's a detail of that setup for when you walk into the lab. You can see how that air pot damper is attached to the load cell here. Here's accelerometer. There's an adjustment here where you can change the level of damping in that air pot dash pot damper. And I've also included on these slides for you to go back and review the specifications. In particular, pay attention to the damping coefficient that the manufacturer provides for this small device. And here are the sizes for you to review. It's a small damper, so you can see it's only about half an inch, 3/4 of an inch in length. By giving you this damping coefficient, they imply that basically the B value is constant, and you can see that's 0.088 newtons per millimeter per second, or about 88 newtons per meter per second. Okay, so we're going to be measuring this directly in the lab, and so you can see that that damping value should be anywhere between 0 to 88 if you use SI units. There's some other parameters here, other specifications that you can review. There's friction in the sliding here, but that's very small. Okay. In summary, here are some of the goals for this lab. Again, you want to use your knowledge of mass spring damper models, system models, to kind of understand the design of the experiment. You want to continue using an accelerometer, so improve your skill in the usage of that sensor. But in particular, what we want to focus on is learning how to make dynamic force measurements. So in a related video, I'll talk more about that, especially about strain gauge principles, which is something that I think all mechanical engineers should have a good understanding of that. Especially how they're used in load cells. So I'll talk about that again in a related video. You're gonna in the lab again increase your lab use skills and also be introduced to some signal processing techniques, filtering, detrending the data. Since your acceleration is going to be integrated, you tend to get a trend in that signal when it is integrated into velocity, and so you'll be talking about that in the lab and how to get rid of that trend.